So we have seen lists which are sequences of a uniform type, and in particular we also looked at strings, which are the special case of lists where the uniform type is character. But very often we need to keep multiple types of data together as a unit. And so this is what in a language like C or C++ would be a struct, okay, or it would be basically a unit of information. So for example, if you want to keep information about a student, you might want to record the name, maybe the roll number and the date of birth together in one place. Right? So if you do that, then you would have a string, okay, and then you have say an int and maybe another string. Now you cannot make this a list because this is not of a uniform type. Now you might want to take a group of such things and make it into a bigger item. For instance, you might want to keep a list of marks for a number of students where you keep the name and the marks together for a given student, and then we have a list of such items. Right? So tuples are Haskell's way of doing this. So remember, notice that we have used here this round bracket, not the square bracket of list. So we have the square bracket which applies to lists, okay, and then a round bracket which allows us to collect together values of different types. So a tuple basically takes some n types and glues it together as a single unit, okay, where we use this round bracket and commas to separate the given parts of the unit, and the types are inherited from the type of the overall tuple is inherited from the underlying type. So if I have a pair of integers 3, minus 21 written in this way, then its type is the tuple or the pair in this case int, int. Whereas if I have three values like this with round brackets, then the first is an int, second is a bool, third is an int. So its type is tuple of int, bool, int. Now, because these types need not be uniform, we could have different structures. For instance, we can have a list as the first component and an integer as the second component. So here we have a tuple which consists of list of int and int. So because the syntax is very structured, there is only one way to decompose a tuple, which is to use the comma to separate it out. So we can directly use pattern matching to extract each component. So if I want to take pairs of integers and add them up, then I can just directly say that the first element of the pair will come out as x in the second. So this is a pattern which matches the tuple. So when I give it as an input, say 7, 12, okay, then 7 will get mapped to x, 12 will get mapped to y because of the pattern matching. And then the answer will be 7 plus 12, which is 19. Now this pattern matching can be combined with other pattern matching, like for lists. So if we want to take the pair, a list of pairs and add them up across the entire list, so I want x1 plus y1, x2 plus y2 and so on, then we use list induction to say that if I have an empty list, of course the sum is 0. If I have a non-empty list, then I have a first value and a second value. So this is the usual list pattern. It says use colon to separate the x from, or the z from the z's, and the z itself is a pair. So use x comma y to split this as two values x and y, and now I just take x plus y as the sum of the first pair and add whatever I get by doing the rest. Right? So tuples are particularly easy to manipulate in terms of programs because it's very easy to split them using patterns to get the individual components. So for example, supposing as before, we had this list of marks of students where each pair consists of a name and the marks for that name. Right? So we have a pair which consists of a string and an int, and we have a list of such pairs. So this is the type of our input. And now we want to look up the name, the marks for a given student. So we are given a name, which is a string, and we are given this list of marks for the entire class, and we want to return those marks that this particular student got. So we use our usual list induction. So if we have no names, then we have not found this name in this list, then we have to return something. So let's assume that everybody gets a positive mark. So as a default value, we can return -1, saying that it was not found. Whereas if we still have marks to process, then we break up the marks list into the rest and the first element. First element, again, because of the structure, we break it up into the name and the marks. We match the given argument p with name. If it matches, we return the marks. If it doesn't match, we skip this value and look up the rest. Right? So this is the familiar list induction, and this is this double level pattern matching. One is to do the list pattern with the colon and then the tuple pattern with the comma. So Haskell gives us a little bit of flexibility in how to refer to these kinds of types. Very often, because we are grouping together these types as a unit, we want to maybe give it a name which makes sense for that unit. So we might want to say, instead of writing list of string comma int, we might want to indicate in our program that this particular unit has some meaningful association for us. So maybe we want to give it a name like a marked list. So Haskell has this declaration called type, which says that the name marked list is a synonym for the name string comma int. So this means that we can now change our earlier definition. So instead of writing here list of string comma int as we had done earlier, once we have this type definition in our program, we can use that instead of this type. Now this is just a synonym. Okay? In the same way that string is the same as list of cards, there is no difference. There is no difference between writing marked list and string of int, list of string comma int. But this is just very useful for us to make our program more legible, and also of course to cut down the amount of stuff that we have to write. And now a nice thing is that if we change this slightly, then everywhere the type remains the same, provided of course the functions are updated to use the new type. So both marked list and list of string comma int are exactly the same type, and string is a type alias. Okay, so this is not like it's creating a new type, it's only creating a new name for a complex type. So here is another example. So supposing we want to represent points in two-dimensional space by xy coordinates. Then a typical xy coordinate will be of type float comma float. It will be a pair of real numbers. We might want to encapsulate this float comma float as a single name and call it, say, a 2D point. So let's use point 2D to refer to this. Then we can compute the usual Euclidean distance between x1, y1 and x2, y2 using Pythagoras formula. Right? You take x2 minus x1 whole square, y2 minus y1 whole square, and take the square root. Right? So the distance between x1, y1 and x2, y2. So now we know that the underlying type is point 2D. Point 2D is itself a tuple. So we can use this pattern matching to extract the coordinates without having to ask what is the first coordinate, what is the second coordinate, and then use these values directly in the function. Okay? So this is an example. Now we could correspondingly expand this to a 3D point and have the three-dimensional version of the distance formula, which includes the z coordinate and so on. So this is an example of how you could use tuples to make your type of your program more meaningful. Now you know that you're taking the distance between points, so it makes your program more legible. Now to illustrate the fact that these are only type aliases, right? Now suppose that we have a function f which takes two floats and produces a point. Now remember that this is just, by our earlier definition, the same as float comma float. So we had this thing which said type point 2D equal to float comma float. So this definition gives us an alias. Now I have another function g which takes float comma float, and produces a float. Okay. So the whole point is that this should be the same as point 2D. There's no difference, we claim, between point 2D and float comma float. And indeed, if I take the value of f produced for some, so I take f of x1, x2, then this produces a point 2D. Again, f y1, y2 produces a point 2D. Now I can feed these to g, which g is expecting only float comma float and float comma. It's not expecting point 2D. But because point 2D and float comma float are exactly the same thing, Haskell will not complain about the type of this. It will say this is well typed. So in every context, if I have a value of 0.2d, it is exactly compatible with any expectation of a value of a tuple float comma float. So these are just different names for the same thing. They are not different things at all. So let's get back to this distance function. Okay? So this particular expression is rather tedious. Okay? So let's say that we want to write a function which actually takes an argument and squares it. So we can introduce a function square. Okay? So we can say square of x takes a float and produces a float, and it just returns x times x. Then this is a much more legible way of writing the same function. right? So it says take the square root of x2 minus x1 square plus the square plus y2 minus y1 square, right? So this is much clearer that this is x2 minus x1 the whole square than the long thing with the multiplication. But now the only problem with this formulation is that we have produced a function sqr which is used in distance but now becomes available everywhere in our program because I have defined it separately. So what we would like is to localize this auxiliary function and push it so that it's available only within distance and doesn't affect the rest of my program. I can or cannot use, may or may not want to use sqr elsewhere. If I want to, I can write it again, but it doesn't conflict with this definition of sqr. So Haskell has this other keyword which we have not seen before called where. So Haskell says you can write square root of x2 minus x1 whole square plus y2 minus y1 whole square and then say where square is the function given below. Okay, so this is a localized definition. Now square is available within distance, but it's not available outside. So distance can make use of square and the function square is defined inside. So it's local, the scope is only within distance. Outside, if I say square, okay, there is no square. So this is an obvious advantage of having local definitions, which is, using this where command, which allows you to localize the definition. A slightly more subtle point is that we might want to avoid duplicating a computation. Right? So here is another use of where. So we have not put square, we have gone back to the multiplied version, but instead of x2 minus x1, we have written xdiff. Instead of y2 minus y1, we have written ydiff. And then we have said xdiff is x2 minus x1, ydiff is y2 minus y1. So notice one other feature here, which is that the values that came into the function are available inside the where. Right? So I have x2 and x1 coming from the function call and they are available inside the where. So I can refer to the arguments of the function inside the where. I can refer to the values defined in the where in the function. So what does this give us? Well, what this says is that if I write xdiff times xdiff as opposed to x2 minus y, here Haskell will actually not recognize, there is no way that Haskell can recognize that this x2 minus x1 is the same as this x2 minus x1. Right? It does not try to optimize any calculation, so it would actually do it twice. Now in a subtraction it may not matter, but if this were a complicated function that had to be called, then if you use the where and give it a new name and use the same expression of the name twice, it knows that it has to compute xdiff, but having you computed xdiff is the same xdiff here. Right? So this is one way in which you can control the efficiency of the program by ensuring that common expressions which occur in multiple parts of your program are evaluated only once for a given set of arguments. So to summarize, what we have seen is that lists have sequences of uniform type, and if we want to combine values which are of different types into single units, then we use tuples. So tuples are written using this notation of round brackets and commas, and then we can use pattern matching to get the individual components when we write function definitions to process tuple data. Along the way, we have also seen two new Haskell constructs, type and where. Type allows us to create new names for old types. So this is a convenience for writing programs and for making programs more legible. Where allows local definitions, and it also helps us to avoid wasteful recomputation of expressions.